Today we're learning about perpendicular bisectors and how they interact with triangles specifically. So to review, a perpendicular bisector is a line or a line segment that intersects a line segment, so that part has to be a line segment, at a right angle, and in doing so, it divides the line segment into two congruent pieces. I'd recommend you redraw that little diagram. Now, in triangles, there's a theorem here that's rather interesting. If a point is on that perpendicular bisector, so here we're labeling that point P, then it has to be equidistant from the endpoints of the line segment. And what this ends up meaning is that if your vertex of the triangle is on the perpendicular bisector, you can assume that this is an isosceles triangle. So here I've added some labels. Angle A is going to be congruent to angle B because it's an isosceles triangle. PA is congruent to PB. And at the top, because it's also bisecting that vertex angle, angle APX and angle BPX are also congruent. Now we can use this information in problems like exercise number 16 from your book. So if you're not sure how to draw this, it's also in your book. Exercise number 16 says if AD is equal to 21, BF is equal to 8, and DF is equal to 8, what is the value of AB? Well, if you think about it, BF and FD make up two sides of the triangle that shares a base with triangle ABD, the big one. And if they're congruent, then that makes that an isosceles triangle, and it also means that we can assume that AC, that line segment that goes through the middle, is the perpendicular bisector. And as long as it's the perpendicular bisector and it keeps going through and goes through A, then AD and AB have to also be congruent. So we can assume that AB is also equal to 21. We're going to also look at angle bisectors. Angle bisectors split an angle in half. Now, any point on the angle bisector, here also labeled P, is equidistant from the two sides of the triangle. So here, whenever we're talking about equidistant from, we're going to assume that it's the shortest distance to that line. And that also happens to be perpendicular to the sides of the angle in this case. So we have this diagram, and I've only added two little markings, the congruent markings from A to P and P to C, just to show that the distance from that point to the sides is the same. Now, the next two diagrams are very complex. I'm going to actually walk you through each one individually, but for now, you can get the text. So, first we looked at perpendicular bisectors. Perpendicular bisectors in a triangle meet at a point, and we call this point a point of concurrency. A point of concurrency is just a point where multiple lines intersect at the same point. Now, in a triangle, this has an interesting property that the point of concurrency in the middle is equidistant from the vertices of the triangle. So PA is equal to PB is equal to PC. Not to be confused with angle bisectors, which are perpendicular, which also meet at a point of concurrency. But they're also going to be equidistant to the sides of the triangle. Okay? So if you've started drawing these triangles, you might want to pause for a second. Just get the text down. And then we're going to show you how to draw the two separate triangles in just a second. So first, perpendicular bisectors. That means we split the sides of the triangle in half, and we draw a line out of them that's perpendicular. They meet at a point, and that point happens to be equidistant to each of the vertices. So to draw the first diagram, you're going to start with a triangle. I usually like an acute triangle for these diagrams. It's just a little easier to work with. You're going to start by trying to find the midpoint on each side. You can just kind of estimate where is the middle of that side, where is the middle of that side, where is the middle of that side. Next, label to show that the two halves are congruent. And then you're going to draw a line to the best of your ability, sketching out at a right angle from that point. So you want it to be perpendicular to the side. And usually the first two will obviously intersect at a point. And then the third one, you can just kind of fudge it and try to get it to meet at the same exact point to show that they have a point of concurrency in the middle. So all three lines should meet at the same point. Make sure to draw in that these are perpendicular to the sides. And last, and you might want a different color for this just to show kind of what the conclusion is. Last, you want to draw from the point of concurrency to each of the vertices. And I didn't mark these as congruent because I was already getting up to 4 markings for congruency, and I just thought that was a little silly. So, but if you'd like to mark them as congruent, you can do 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. To show that all 3 lines from the point of concurrency to the vertices are congruent. Next, we're going to draw the diagram for angle bisectors. So just like it said, we're going to start with the angles this time. Now, instead of splitting the sides in half, we're splitting the angles in half. So starting at whichever vertex you choose, trying to draw a line sketching out that goes right through the middle of the angle. Repeat for the other 2 angles, and just like before, we want them to meet at one single point. So if you need to fudge it a little bit because you're hand drawing it, that's okay. Just make sure it looks realistic. Last, we can conclude from this that the distance from the point of concurrency, which I labeled Q here just to make sure it's different from the other one, is equidistant to the sides. So we're trying to find the shortest distance from that point to the side, and it should look like it's perpendicular to the side if you've done it correctly. So the shortest distance from this point to N, from Q to N, ends up being perpendicular to the side YZ. Last, I labeled the 3 points where it meets, and you can add a congruency marking here to show that those 3 are also equidistant or congruent.